Yeah. I didn't hear you. What? Yeah, sure. Okay. So now that you've had the opportunity to do one of those take-homes, what did y'all think? You like it? I hope that at least with that first one, you get an idea of kind of the time management that's going to be required. So on the next one, you'll be a little bit more prepared, I guess, to, you kind of know what you're getting. I did have a good amount of you reach out for help, which is good. I am very, very willing to help you. But as we get closer to the due date, I start to become less patient. So like if it's Sunday night and it's due on Monday, like I have less patience than I do if you ask me a week ahead of time. Yeah. Or if you come on my office this morning and you're asking for help on a problem that you haven't really gotten really much work done on. So, all right, well, we need to move on. 10.6, we did that real fast at the end of class last time, and it was just recognition of the quadratic surfaces, and the homework assignment for that, I wasn't sure if you had the correct homework assignment there. I think the page number was wrong on the notes, but I'm just going to verify right now that for 10.6, you should be doing, come on. It's page 579, 21 through 27 odds. So this is for 10.6. What did I just say? 527? 579, sorry. 579, 21 through 27. Did anybody actually get that homework done? Was it straightforward? Pretty straightforward? Just a little completing of the square in there? Okay. All right. I also did notice that some of you have kind of fallen behind on the homework. And just keep in mind that the take-home exams will be significantly easier if you've got the homework done, because that is where you get all like the basic stuff out of the way. And then on the take-home, it gives you just a little bit of a clearer picture of what you're supposed to do. So I can't force you to do your homework. I guess I could grade it, but it's Cal 3. You should do your homework, right? All right. Let's get going. We are going to move into vector functions today and space curves. Sounds fancy, doesn't it? So we'll start with a couple of definitions. What is a vector function? So any function r of t, now notice we have the vector notation on the r. Have we seen that before? Have we seen that vector notation? That's what we used for lines, didn't we? Yeah. We use that same notation. So what I'm going to show you here in a second is that a line is an example of a vector function. But in a more general sense, a vector function is any function that has either 2 or 3 components to it, right? Like vectors, 2 vectors or 3 vectors, where each of the components of the vector are generated by functions of the variable t. Now t here is a real number, so it's kind of like a clock that's running in the background. And so you can think of it almost as time. It's not always time, but I'm just saying you could think of t as something that you don't see on the picture, but it's running in the background. And then what happens is that each of these components, we call these component functions, kind of tell you where your vector is going to be. And notice that these 2 functions, or in the case that you have 3-dimensional, these 3 functions, f, g, and h, are completely independent of one another. So they don't really know what the other component functions are doing, right? G has no idea what f is doing, f has no idea what h is doing, and so they're kind of independent from one another, all right? Anytime we have a vector function as defined, here, we call them vector functions or vector valued functions. That's just terminology here. Whenever we are looking at vector functions, the domain are real numbers, so we're taking in real numbers and we're spitting out vectors. And those vectors are either going to be two-dimensional or three-dimensional. So this is different than a traditional function like f of x equals sine x. That function took in a number, spit out a number. Here we take in a number, spit out a vector. I just said this a second ago, but here's the actual note that says it. These are called component functions. All right, component functions. And then we can talk about what the graph of a vector function is. So like if you are given a vector function, you're asked to graph it, what's it going to look like? So we all need to understand here that vector functions in either two or three-dimensional space are going to be curves. Okay, they're not surfaces or anything like that. It's going to be a curve. Now, it might be a straight line, and we'll just kind of call that a curve. But the important thing is it's almost like you're taking your pencil and you're drawing something out in either two-dimensional or three-dimensional space. So here's an example of a vector function. Now this is a two-dimensional vector function because it has two component functions. So what are the component functions here? T squared and then 1 minus t cubed. So if I ask the computer to graph this for me, that means start plugging in values of t, it's going to spit out vectors, right? So let's see what would happen if I plugged in t as 0 into this. We get r of 0, we get 0, 1, right? And that's a vector. So you can see that vector right here, the vector 0, 1. And it's pointing to that point. And we can say that that point right there is a point on my curve. And then as I let time go by, I start to draw the rest of the curve. So as t changes, the vector changes, and you draw the rest of that curve out, right? I actually don't know what all this is. Oh, I had it where it can change the colors. Oh, that's cute. Big deal. All right, and here's the actual vector. So do you see that the curve is generated from the position of all those vectors, all right? That's just exactly the way we did the lines, right? When we were drawing the lines, it's the same exact principle. But it doesn't have to be straight. Did I miss one there? I feel like I missed one. No? Okay. That was it right there. Let's look at this one. Now, if you have your notes printed, you're going to know what this looks like. But if you don't, and we're just looking at this for the first time, let's try and guess what this is going to look like. What is cosine t sine t? Do you remember this from pre-cal? Yeah, if we look at that, if in pre-cal if we had this actual relationship, it was x was cosine t, y was sine t. This was how we actually got familiar with the idea of the unit circle, radius 1. And if this was the angle t, then the x-coordinate and the y-coordinate were actually defined this way. So if I let t be 0, I'm going to start here, and then if I let t start getting bigger, it's going to start drawing me the circle. So these first two component functions, cosine t, sine t, should be something that you're familiar with. And they're going to keep popping up. Anytime you see cosine t, sine t like that, you need to start thinking circle, 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 right? So this should be drawing me a circle in the xy plane. But it also has a z component. So this is trying to draw me circles like a vector in the xy plane. But the z keeps on getting what? What happens to the z component as t gets bigger? It's t divided by 5. So it's going to be just some number divided by 5. So as t gets big, that number starts to get big, doesn't it? Because 5 is fixed. So imagine trying to draw a circle, but at the same time, your z component starts getting bigger. And do y'all see it? It's kind of like a spring. This is it right here. Actually, this is too big. So there it is. So if we look at it from the top, if we look at it from like straight down, you can see the cylinder, right? The circle that it's trying to draw. But because the z component is growing, it kind of stretches that circle out as it draws it.
And the vector stays fixed at the origin.
Yes, the vector will always be referenced back to the origin. So let me play this and see what happens here.
Does it?
Yeah, I don't know why. For some reason, when I go off screen, it doesn't like it. There we go. So there it is. It's drawing the vector. So the vector is trying to draw the circle, but it keeps getting taller. Does this make sense? All right, now, at this point, I want to just kind of remind you about what we did in Calculus 1. So when you took college algebra, you learned about functions, right? You learned about the polynomial functions, all the power functions, exponential functions, logarithmic functions. You get to pre-cal, you start learning about the trig functions, sine, cosine, tangent, right? All those. Then you get to calculus. They say, hey, welcome to calculus. There's this thing called the limit, right? And you start applying the limit to all these different functions. And then you do the derivative, right? And then you do integration. So if someone hands you a function, you should be able to differentiate and integrate it. Well, now we have a new type of function. It's called a vector-valued function. And so we're going to ask ourselves the same questions. Can we take a limit? Can we take a derivative? Can we integrate it? What does it mean, right? What are these things? What's the physical meaning to those things? And also, the definition of continuity. So everything that we've done in Cal 1 and Cal 2 is now on the table because we have a new kind of function. So we'll talk about limits first. And you're going to really love the result here because it's not complicated. At least it doesn't look complicated. Does it? No. Given a function, a vector-valued function, which has two components, right? Or three, then we define the limit as follows. So if you want to know the limit as t approaches a of the vector-valued function, all you have to do is take the limit of each of the component functions individually. And since each of the component functions is just like a traditional function from algebra or pre-cal, you just got to be able to take limits, which you've already demonstrated. You're here, right? So that means you're limit masters? Yeah. We're about to find out.
We took that information and threw it away.
Yep. At one point in time, you were decent at limits. Okay, so just take the limit of the component function. That's all you have to do. And here's the first example. All right. So find the limit as t goes to 0 of this vector-valued function. So I guess I'll use some appropriate notation right now. I'm going to say that the limit as t approaches 0 of r of t is equivalent to the limit as t approaches 0 of the first component function, which is cosine t, comma, the limit as t approaches 0 of the second component function, sine t over t, and then finally the limit as t goes to 0 of the third component function, which is e to the t minus 1 over t. All right, we get to do some limits. So what is the limit? It's coming. What is the limit of cosine t as t goes to 0? So cosine of 0 is 1, right? So there's no problem there? That's headed to 1. Good. That's great. So far, I'm going to say 1. And then, how about this one? 1 again. Why is that 1? You can do L'Hopital's rule, or in Cal 1, you're actually given this limit sometime in the early part of the class, and you're told, remember this limit, it comes up all the time, we're going to use it, and the limit is 1. And then later on, you're shown L'Hopital's rule, and you can prove it with L'Hopital's rule by just, what is L'Hopital's rule again?
If it's like an indefinite form.
Okay. Yeah, so L'Hopital's rule is spelt like La Hospital. Okay, L'Hopital's rule says that if you take a limit, okay, if in the limit, that's what I'm going to say, in the limit, you have 0 over 0 or infinity over infinity, only those two forms, you can only use L'Hopital's rule if your limit looks like one of these two forms. Okay, if it looks like something else, you might have to do something to make it look like this first. But if you have that, then what can you do? Then take derivative of top and bottom separately. Then I'm going to put derivative, top, bottom. That says bottom. Blah, blah, blah. I'm not here to reteach L'Hopital, okay? Blah, blah. But that's the rule, okay? We're looking for 0 over 0 or infinity over infinity. So when we look at sine of t over t, and t goes to 0, sine of 0 is 0, t is 0, so we get 0 over 0. So apply L'Hopital's rule. Take the derivative of the top and bottom separately. So I'll do that right here. Let's do, if I'm using L'Hopital's rule, some books put an H here, some books put an H and circle it, and for some reason I didn't get that memo. I put an L and circle it for L'Hopital. And then limit t goes to 0. I take the derivative of top and bottom, cosine t over 1. And now when you take that limit, you get 1 over 1. And whatever the answer is here is the same as the answer here. That's what L'Hopital's rule gives us. It's a great thing. So we get 1 here. And then what about this one? L'Hopital again, right? T is 0, e to the 0 is 1. 1 minus 1 is 0. So we get 0 divided by 0 again. L'Hopital. Let's just do a quick L'Hopital here. What would we get? Derivative of the top? E to the t over the bottom. 1. And now let t go to 0? Get 1. So you just get the vector 1, 1, 1. Now, what is important, all right, one of the things that's important to understand here is that we are not saying this, are we? We are not saying that when you plug 0 into the vector function, it spits out the vector 1, 1, 1. We're saying that as you get closer to 0, that it gets closer to that. But at 0, this vector function is undefined, right? Isn't this vector function undefined at 0? Absolutely. You cannot plug 0 in here. You cannot plug 0 in here. But we still have the concept of the function is approaching something, right? It's getting closer to that vector. All right, any questions on that? You're going to need to go back. I'm pretty sure that you're going to need to go back and review L'Hopital's rule. Unless you're really comfortable with it, there are some problems that I'm going to give you. I know the next take-home exam has some problems where when you do these limits, it's going to be a little bit more involved than just 0 over 0 or infinity over infinity. It'll be one of those other indeterminate forms like 0 to the 0 or like infinity to the 0. And you have to do some other stuff before you do L'Hopital. So just be prepared that you might have to go back and review the indeterminate forms, which is in chapter, I don't know what chapter it's in, but
You'll find it.
yeah, you'll find it. And I have, on my YouTube channel, I have my Cal 1 playlist. I do have an entire lecture on L'Hopital's rule that you could go and look at if you were so inclined, if you needed to. All right, so the limits are straightforward. In terms of what you do, it's straightforward. Can you do the limits? That's a different question. All right, continuity. So when it comes to continuity, the definition of continuity is exactly the same as it was for a regular function. To say a function back in Cal 1 was continuous at a meant the limit as x approached a of the function was equal to f of a, which just meant that visually, back in Cal 1, okay, back in Cal 1 it said this. To say that a function is continuous at a meant that as you come in from the left and you come in from the right, you're headed to the same point, all right? That meant the limit existed at a. And to be continuous there, you actually had to be defined, your function had to be defined, and it had to actually match where it was headed. Because it was possible in Cal 1 for this to happen. Would this limit exist?
Yes.
No, would this limit exist? The limit would exist, right? Because coming in from the left and from the right, they're headed to the same place, but it would not be continuous because where it's headed doesn't match with what it's defined to be. To make it continuous, you actually have to move that point down here. That's continuity. This is the same exact thing happening with vector functions. It's, just take it off that flat sheet of paper and just make it a curve sitting out in space. What we need is for that hole to be filled in. Okay, they have to head to the same place and fill the hole. We won't do really any work with continuity with these vector functions. I just want to make sure that the definition is stated, that there's nothing crazy happening with continuity. All right, we want to describe this curve. Describe the curve given by this vector function. What I'm really asking here is to see if you recognize this curve. It's a line? How do you know it's a line? Yeah, it follows the format of a line. Let's see. If I wanted to, couldn't I split this up like this? 1, 2, 0, plus t, and then what? -1, 4, -6. That's the vector equation of a line, right? You have kind of like the initial point, like a starting point, then you've got a direction vector, and then you've got your t. That's where when we started with vector equations of the lines, that's what we started with, right? But if we put it all together and just write it like this is a vector valued function. That's what I was saying earlier. Lines are vector valued functions. Now, we could argue, is that a curve? We would still call it a space curve. It is a curve in space. It just actually doesn't have curvature to it. But it's a curve in the sense that it's not a surface or a solid or something like that. All right, so that's all. Just recognizing that that's a line. That's all that's about. All right, this, again, is something we've done, but let's just make sure we remember how to do it. How could you find the vector function for the line segment? That means it just draws the line between these 2 points. Okay, we're going to have to restrict the domain, right? And I said that I like restricting between 0 and 1. Remember me saying that? T between 0 and 1. But if you're going to do it that way, you have to make sure you set it up correctly. So I'm going to need to put in here R of t is R naught plus TV, like that, right? Did I ever tell you my Cal 3 professor had a different equation for that? I think it was something like this. It was R of t equals u, the vector u plus TV. He used the vector u instead. The couch potato formula. That's the way he helped us remember the couch potato formula. U plus a TV, right? U and a TV, couch potato. That's the vector equation of a line. I've replaced it by R naught instead of U just because the book uses R naught, so I wanted to be consistent. But I always remember it. Look, you've got a vector, takes you out to the line somewhere, you add TV, and then you've got your line. That's useless information. I'm just sharing that with you. Okay, so if you're going to use this format, if we want to do a line segment, and we want to go from here to here, so the word to is important here, then what am I going to use for my R naught? 359. That you wouldn't have a choice on, because that R naught needs to be not just either point, the one you're going to start at. So this is going to become 359, and I'm going to go plus t. Now my direction vector is the vector that goes from 359 to -57, -3. So you've got to create that vector now, right? So subtract, what should I get here? -8, 2, -12. Okay, that's all good, but now my restriction. T is an element of the interval 0, 1, or if you like, you can write t greater than or equal to 0, less than or equal to 1. Either way, you need to somehow restrict your domain. That way it just draws the line segment. And you can always check your work. Just plug in 0 for t, and it should wipe this whole thing out, and we should be here, which is the first point. And then plug in 1, plug 1 in for t here, and put them together, and you should be at -5, 7, -3. And then any value between should be between those 2 points on a straight line.
So in order to get the domain, always should be 0, 1.
You got it?
Use the vector, direction vector
Then you have to pay attention to where you're starting and ending, okay? If they didn't care about where it went from, you could have picked this one, but then you need the vector going from here to here. So you'd subtract. You take this one, subtract this one. If you want to stick with 0, 1, that's what you need to do. I like sticking with 0, 1 because it makes it easier, you know. Those two endpoints are easy to work with, right? 0 and 1. The book does do that kind of a different way. I've never liked it, so that's why I show it that way. Okay, find the vector function and its domain. Oh, this problem just comes out of nowhere. You're like, what? How am I supposed to answer this question? Like, is this even the same class I'm in right now? Like, all of a sudden we jump to this. Find the vector function and its domain representing the intersection of these two cylinders. Whoa.
Question.
Yes.
So obviously domain before in 2D was x values and range y values. Or something different.
Well, if we're finding the question is about the domain, if you know, in traditionally it's x and y values. Here, we're trying to find the domain of a vector valued function. Vector valued functions take in t, right? T is what goes in. So when we say domain, we want what are the restrictions on t? Okay? So let's appreciate the problem first. And do I have a picture? I think I have a picture. Oh, I have a picture. Yes, I do. Here are the two cylinders we're talking about. All right? We have two cylinders sitting in three-dimensional space. Now, I know that I've got two cylinders because I told you, but also because from the last section, 10.6, you should recognize those equations as cylinders. Do you recognize those as cylinders? Okay. Now, you might say that, wait a minute, this looks like a circle. X squared plus y squared is 9. And I would agree with you. That is a circle in two-dimensional space. But in three-dimensional space, it's a cylinder because you have a free variable, right? Here, this is another cylinder. It's a circle, yes, in two-dimensional space, but you're missing the x, which means you have another free variable. So this one opens out the x-axis. This one opens up the z-axis. So you've got these two cylinders, one radius 3, one radius 2, yeah? And what you're looking for here is their intersection, which is that blue curve. Can you see that blue curve there? And there's one on the other side. Now, if you can't see it, let me just pull the cylinders back a little bit so you can see through them. Okay, you see those two blue curves? Yeah? I think this is just crazy, that what I'm asking you to do here, but I'm asking you to give me the vector function that draws those blue curves. Doesn't that seem like quite a step up right now from like, hey, here's 2 points, find the line segment? Doesn't this seem like this would be pretty challenging? I mean, I think it is. And I like to think about this problem like from a real world perspective, because we always ask that question, like, why is this important? Why is this relevant? But, you know, let's say that your company builds pipes for something, right? Like huge steel pipes. And that blue would represent your weld, right? You'd have to weld these pipes together. And you might be interested in the length of that weld. Or you might want to program, most welds are done by machines nowadays, like the ones in factories. So you have to program some, mechanical arm to come out here and weld this, right? It needs to know the path. And that blue curve will be the path, right? So how do we generate that? That's it? Okay, that's fine. Okay. Does it seem difficult? Anyone have any ideas? I mean, this is all you got to work with right here.
So can you just like, we have x and y, we just write down its equation,
Mm-hmm.
its vector equation, and then find z in terms, because z is related to y somehow, so find z in terms of y and then substitute that as well in the vector equation.
Yes, you're on the right track here. Because I guess part of what you're saying, maybe, and correct me if I'm wrong, is that if you're on the blue curve, you have to satisfy both of those at the same time. So whatever we pick for our x and whatever we pick for our y, whatever those are, when I plug those in, they have to satisfy both of these. And what you're saying is that since y is here and y is here, you should be able to solve this one for z and get it in terms of y, or something like that, or swap out. You're definitely on the right track.
Could you put it into a system of equations?
System of equations, you would only have 2 equations, you would have 3 unknowns. Let me try and do this, picture-wise. Yeah, we do need a t, right? We need, at the end of this, to have like, remember what we're looking for here. R of t equals f of t, g of t, h of t. That's what we need, right? I need 3 component functions that will draw that blue curve. So here, let me do this. Let's figure out which of these is the, which one's opening out the x-axis and which one is opening out the z-axis.
Green rainbow.
The green, what's the radius of that green one? 2. Let me go back to the thing here. So that radius, this one's the green one, right? And then this one is the other one. And that green one was opening out the x-axis. I'm going to have to. All right. Okay. We good with this? X-axis, y-axis, z-axis. So the reason I wanted to bring this picture up is because I thought this might help. What if I rotate this and we look at it straight on, like we're looking straight down the x-axis? What do we see? All we see is circle, right? All we see is that circle. I know it's a little off because our viewpoint, the way the computer does it, it kind of has like a funneling effect. But if we were to truly be able to go all the way out to infinity and turn around and look back down the x-axis, all we would see was a circle, right? Can you draw that circle? How would you draw that circle? What plane are we working with here? So what's this axis and what's this axis? This is the YZ plane. Can you draw me a circle of radius 2 in the YZ plane? You need to do it using functions of t. 2 cosine t, 2 sine t. Remember a second ago I put this up on the board and I said you're going to need to remember these from pre-cal. This draws you the unit circle and this has become very important to us. Okay, we're going to use the same philosophy here, except we're not going to use x and y because we want to be able to draw this in the YZ plane, right? So here's what I know so far. For my vector valued function, I need to draw a circle of radius 2 in the YZ plane. So I'm going to do 2 cosine t, 2 sine t. Now, just for clarification, which equation was I using to get that information here? For this piece right here came from the y squared plus z squared equals 4, right? Agreed? So if that's all I had to do was draw that circle, that's what I would do, right? I would do this. But my x coordinate is free here, right? And that's what drew me the cylinder. Now I cannot let that x coordinate, that x component function be free because it has to now follow this. So let's turn it and let's kind of look at the x coordinates from the side. What can you tell me about these x coordinates? So this is the x, left and right now. I have to be following this kind of curve right here, like this, right? Don't I? So that's not just allowed to be whatever I want it to be. But what can you tell me about that blue curve? Where does this blue curve, we know that the blue curve lands on the green because this guarantees it, right? We're on the green one because of this. We also have to be on this one, don't we? It looks hyperbolic, doesn't it?
Instead of y in that first equation, we put 2 cosine t.
Instead of what? Right here?
In the first equation,
Okay, so you're saying, look, we've got to live on this cylinder at the same time, right? We're already covered here. We're on this cylinder. But we got to live on this one now. And you're saying take this one and
instead of y, put 2
instead of y, put 2 cosine
cosine t.
t?
So we can find x.
Okay, so come here and say we want to know the x coordinate, don't we? This equation has x in it. So we could say this. Couldn't you say that? X is 9 minus y squared. Just move the y squared over. But you know what y has to be. Y has to be this, right? So I can replace y with 2 cosine t. And I get x squared is what? 9 minus 4 cosine squared t. So I'm plugging in 2 cosine t in for y, squaring the 2 and the cosine. And I almost have x, don't I? Just square root both sides. And when I square root, I'm going to have to do plus or minus. Now, when you do plus or minus, are you thinking that's good right now or bad? It's good, because how many blue curves did we see? 2. And this plus or minus is going to generate both of them. The positive one's going to generate one of them, and the negative one's going to generate the other one. So this piece right here is our x component function. There's actually 2 of them. Y'all see how that worked? We drew one of the circles, right? We drew the circle on the cylinder, and then we used the other missing component, we used the other equation to come back in, isolate the variable we're trying to figure out, and then use what we know about the other variable here to figure it out. So now everything is in terms of t, isn't it? So let me write down our final vector function. R of t is equal to plus or minus the square root 9 minus 4 cosine squared t, and then we have 2 cosine t, and then 2 sine t, and that's it. There are 2 functions there. Everyone understand that? There are 2 functions. We're almost done. Well, kind of. We still have a lot of work to do, actually. We still need to figure out the domain. What is the domain of this function? And you're going to run into a problem here because you have square roots. Doing okay? What do you need for sure to happen here? We need to make sure that 9 minus 4 cosine squared t is always greater than or equal to 0, right? We need to make sure that that never has a problem. See, we have a radical root function here, don't we? We have a root function. So anytime you have a root, we can't have a negative underneath. So we need to make sure that the radicand, the thing underneath it, is always positive or 0.
I think if cosine squared goes to 0, it's not 1.
So what?
Cosine squared of 0 is what, 1? So t would have to be 1, or 0 to 1. For it to be, for that equation to be greater or equal to 0.
We would need this, right? Algebraically, just move the cosine squared part over, right? Agree? Divide by 4. What can you tell me about this? I need cosine squared t to always be less than or equal to 9/4.
Cosine between -3/2 and 3/2.
Yeah, this is going to have something to do with 3/2 or something like that. How?
Because you take the
Positive.
square root of both sides. And you get, yeah, 3.
Yeah, we have to be careful though, because the way we solve inequalities is a little bit different than the way we solve equalities, right? I mean, we have to be very careful with signs because it flips inequalities over. So here's what I'm going to do. Because of the inequality, I'm going to come in here and just to be safe, I'm going to change my inequality to equality. That's the way the standard way we approach inequalities is that we get where is it equal first, and then we go test regions. So let's restart this with this equation. Equation, not inequality. I'm asking myself this, which turns out to be when is this true, right? And then square root both sides, so I have a plus or minus again. And at this point, what can you tell me? It's not possible, right? That's not possible. Because cosine is bounded, isn't it? Cosine is bounded between -1 and 1. This is 1.5. -1.5 and 1.5. There's no way that's happening. Which means you don't have any problems. You can plug any t in, it's not going to matter. It's never going to spit out anything bad. Right? I mean, you can kind of see it right here. Look, I mean, like, the biggest this is ever going to get is 1, right? 4 times 1, I mean, 9 times 4, you can take the root of that. It's not a problem. So do we have any domain restrictions there? No? It means you can plug in t, any t, and it's going to be okay. Pardon? There's no domain restrictions on cosine t, and no domain restrictions on sine t. It's just going to keep drawing it over and over and over, right?
That kind of makes sense, though, because
So then
if
how
we,
would we restrict it for just one pass?
Okay, now that's a different question. If you wanted to just draw it one time, then, well, what do you think you'd have to do?
Focus on the X and Y since I think quality was
You need to just be able to draw the circle once, right? 0 to 2 pi? Check it. Let me see here if I'm not asking that question. Let me see here. Let me get this out. What you'll notice is what I have up here is notice I do have some domain restrictions here. Do y'all see those domain restrictions? I have my vectors here. I'm going to take the cylinders completely out of the picture, okay? And I'm going to rotate this back out so you can kind of see it. What you'll notice here is that if I draw this, if I let my t be between negative 41.8 degrees and positive 41.8 degrees, I draw the left side, I guess you could say. And then if I let my t restriction be something else, it draws that right side. Okay, the reason why it's like this is because I set this problem up different than the way we just set it up. Okay, so would y'all like to at least see that setup?
Sure.
Okay, let me bring up my code that draws that, and it's because I don't remember how I actually set it up. There's several ways you can do this, so let me just look for it real quick. Okay, I did it that way. That's interesting. I kind of like it the way we did it in class today. It's going to draw the same thing. Okay, so the way I did it is I didn't even try and like look at a picture, because a lot of times you're not going to have the picture, right? So you're just going to have those two cylinders. You're going to be like, all right, I need to figure out how I can draw the intersection. So instead of trying to use this one first and draw that circle, I did this one. So I said, all right, I'm going to try and draw this circle first. So r of t will be equal to 3 cosine t, 3 sine t. And notice that I'm using the x and y components for my cosine and sine functions. Do y'all see why? Because it's xy, right? And it's 9, so the radius is 3, so I'm using 3 and 3. Yes? Now, if I try and find my z component, I have to come into this equation and solve for z. So if I solve for z, I'm going to get z is equal to plus or minus the square root of 4 minus y squared. But what's y? 3 sine t. So this is going to be plus or minus square root of 4 minus 9 sine squared t. And this way of doing it, which is different than the way I just did it a second ago, we do have domain problems here. We do have domain restrictions. Do y'all see it? Because they're flipped. Huh?
Is that why in your code it stopped at those points?
I had to do that when I wrote the code up. Because when I first set up this problem, this is the way I did it. What I need you all to understand is that these two functions, the one I gave you before and this one, will draw the same curve. All right? But this one has domain restrictions as opposed to the other one has no domain restrictions. So what about the domain restriction here? So 0 to 2 pi should do it. Because you just have to draw that circle one time, right?
So with this one,
It's
because 9 times, let's say sine is stuck at between 1, 9 times 1,
you're going to get a negative under the root, yeah. So what we would have to do here is we'd have to figure out when is 4 minus 9 sine squared t equal to 0. And then from there, move things around. You should get 4/9 equals sine squared t. This is just algebra, right? Moving things around. And then take your square root. So 2/3 plus or minus is sine t. And then what you would do is arc sine on both sides here. And that's where I got the 41.8 degrees and then the other one. And I mean, there's a little more involved with that because you have to almost look at it like a number line with your t. You have to figure out like what regions are valid and which ones aren't. But that's how that happened. The main point of this problem is that if you have two quadratic surfaces, that you might be able to find the intersection of the two. If things work out right, you can do this. How about let's try something a little different. And I was not prepared to do this, but let's see if this is hard or easy. All right, so this was not planned, but hey, got to be ready for anything, right? See, find a vector function which represents the intersection of x squared plus z squared equals 25 and x minus 3y plus 4z equals 10. So what am I asking you to find? The intersection of what two things? Close? Cylinder and a plane. We have a cylinder and a plane. This is a cylinder. It opens out the z-axis, doesn't it? I mean, sorry, y-axis. So here's the y-axis. Y is missing. So we have some cylinder like this. It has a radius of 5. And then we have some plane, right? That's going to come and, I don't know, this plane is tilted. We know the normal vector of this plane, right? Normal vector is 1, negative 3, 4, but really that's just the normal, and I don't know where that is here. But that plane should cut through somewhere, right? So we got this plane, slices through this. What does it look like we would get if we sliced that somehow with a plane? Probably some ellipse, right? But I want the r of t, the vector function, which will draw that ellipse. And again, that seems difficult, but it actually is not that difficult. If one of these is a cylinder, it's actually really easy for us to do this. We're going to follow the same rules. We're going to say our r of t I'm going to try and draw the circle first, or the cylinder first. So 5 cosine t for my x component, and then 5 sine t for my z component, because that my cylinder, right, the circles I'm drawing are in the xz plane, and then there's moved out on the y-axis. So the y is free, but not quite free, right? The y has to follow this.
Question,
Yes?
does it matter if you change cosine and sine, like 5 first?
It won't actually matter. It'll still draw a circle. It's just where it starts. When you put 5 cosine t sine t, it starts here and goes around like that. If you do it the other way, sine t first and cosine, it just starts you at a different point. But it still draws the whole circle. But cosine t sine t is kind of the standard. If you start doing things other than that, you probably might get yourself messed up later. All right, what about the z here? I mean, not the z, the y component. Yeah, take the plane equation, solve it for y. So what do you get when you solve for y? It's going to be ugly, but what's y equal to? 10 minus x minus, I'm missing something.
It should be 10 over 3 minus.
I didn't know if you wanted me to do it all like this, like that, is that right? Move it over,
Divided by -3.
and then divide by -3. It doesn't, yeah, we'll do it that way. Is that right?
Yes.
Now, what? Plug this into here, right? But replace x with 5 cosine t and replace y with, or sorry, z with 5 sine t. So this middle piece right here will be 10, I'm going to have to squeeze this in here, minus 5 cosine t minus 4 times 5 sine t all over -3. You'll see where that came from? No? Yes? No? Yes. That's 20. It'll be 20.
So for something like this, obviously we're not going to run into issues with domain because there's no square root. So when
Yeah, there's no square root here.
so what kind of domain questions would we get? Would we get that whole, hey, what's the domain restriction?
I don't think I would really ask you a domain restriction on something like this. Because all it's going to do is keep drawing the same thing over and over. I'm going to plot this. The original one was x squared plus z squared equals 25. Okay, so to draw that, I need hang tight here. I'm going to pass around the sign-in sheet in just a minute. I just thought it'd be worth it for us to look at this. Jeez. See if I at least get this to plot. Okay, so there's the cylinder. Now the plane, right, was next. And we have, what was the equation there? I need to solve it actually for z. So 10 minus x plus 3y, right, all over 4. Let's see what it does with that. I forgot to put divide by 4. There's probably a faster way I could do this, but I feel better when I just create it myself instead of going to Wolfram Alpha. Okay. that no good? What is going on? I always remember sitting in class when the professor would go do something like this, and I'd be like, jeez. Where is it? 3D. Plot 3D. Oh, I think I was just missing my comma. That's it. Syntax. I'm just trying to convince you we got this. All right, so there's the plane and there's the plane and the cylinder, all right? Now finally, parametric plot 3D. So we had, what was it, 5 cosine t, and then 10 minus 5 cosine t. Keep going. Oh, so we'll just go 20 divided by what? Divided by -3. Oh, all right, almost there. Missing a comma. There it is. I don't know if that makes you feel better, but there it is. Can y'all see it? Hey, you can't really see that, can you? Can y'all see the blue curve here? That blue curve right there?
Yeah.
That's the graph of this vector function. So it kind of gives you some feeling that we were able to do it. All right.
Visual confirmations are always the
Yep. Yeah. Especially when I just make up a problem out of the air. It's nice to have a visual. All right, now, as you might imagine, when it comes to vector functions, they can get pretty complicated, right? Because you can basically draw anything in three-dimensional space, right? Just moving around anywhere. So we like to use examples, computers, to show us some pretty cool examples. So here's one of them. This is called a toroidal spiral. So if you've ever heard of a torus is a donut, basically. And this is a spiral that's going around a torus. And it's kind of cool if you let T go, it starts drawing this spiral, but it's wrapping around this donut shape as it goes. Toroidal spiral.
Is there a donut like that?
Donut what?
Isn't there a donut like that?
What do you mean?
Like actual donut.
There's an actual donut that does that.
Oh, there is? Here's the vector function. I know it's hard to see it here, but I'll just read it out. The x component is the quantity 4 plus sine 20t, just use t instead of r, that quantity times cosine t. That's your x component. Then your y component is this, and your z component is this. And if you were to do that and graph it, that's how you get that toroidal spiral. Very complicated function, but it draws something kind of neat.